This video shows three things: an ATtiny 1614 acting as an I2C slave, a CP2112 USB to I2C bridge acting as the USB master, and a TXS0108E converting between the CP2112's 3.3 volt signals and the ATtiny's 5 volt signals. Recently, I built a board on which an ATtiny 1614 uses Charlieplexing to control 20 LEDs with 5 signals. See link below to my video on Charlieplexing. The 1614 on my board is a 14-pin microcontroller, so I pinned 6 unused pins out to a header with the idea that I would test the ATtiny's ability to act as an I2C slave. This needs 2 of the pins. I use an Ubuntu Linux PC to control the LEDs on the Charlieplexing board. This means that I need a USB to I2C bridge. I use a CP2112 board for this purpose, but it uses 3.3 volt signaling while I want the ATtiny to run at 5 volts. So I also need a bidirectional signal level converter. A TXS0108E does the trick nicely. It then connects to the I2C pins on the ATtiny. This all works very easily. Ubuntu already includes a CP2112 driver. The TXS0108E just works. And configuring an ATtiny Series 1 or 2 microcontroller to work as an I2C slave is very easy. But the software to implement a register-based programming model on the ATtiny I2C slave is a little weird. This is one of the reasons I made this video. Because I'm running the ATtiny with VDD at 5 volts, the level converter really is needed. Signals must reach at least 0.7 times VDD, or 3.5 volts, to be reliably recognized as high. But the signals from the I2C master are only 3.3 volt. Also, many I2C master devices with 3.3 volt VDDs cannot tolerate 5 volts, so the level converter is not optional. Of course, I could have run my ATtiny at 3.3 volts. Then I would not need the level converter, but I would have to drop the ATtiny's speed to roughly 13 MHz, and my LEDs would be less bright. As an off-topic aside, ATtinys running with a VDD of 3.3 volts are also not 5 volt tolerant. Their input signal limit is VDD plus 0.5 volts, or 3.7 volts. Here's the system in action. The Linux PC is commanding the LEDs to blink in an interesting pattern. Since the connections are so simple, there is little else to do but have a quick look at software. Many I2C slave devices use a register-based programming model. I'm going to do this on my ATtiny LED board to show how it's done. The process is a little weird. The ATtiny I2C slave will implement 4 registers, each 1 byte wide. The first 3 registers hold the value to display on the LEDs. The last register is special. Any value written to it causes the LEDs to start displaying the value from the first 3 registers. As an example, to light only the first LED on the board, the I2C master writes 1 to register 0, zeros to registers 1 and 2, and then any value to register 3. Which on Linux we can do with these commands. So I'll just run that file and do those 4 I2C set commands, and we can see that the first LED comes on. Here's the software on the ATtiny, and you can see that we have to include wire.h to use I2C as a master or a slave. Of course, we're using it as a slave in this video. And then you have to define the slave's address. So the master will use that address when it wants to do transactions to the slave. And then, let's see, on ATtinys, the default I2C pins are fixed. And so on 14-pin devices, SCL is PB0 and SDA is PB1. And so you should check your datasheet to be sure you know which pins are used for I2C on your device. Now, let's scroll down to Setup, which is way at the bottom of the file. And these are the 3 calls that are fundamental to using an I2C slave on an ATtiny. So this first one defines a function that will be called whenever the master does a write to the slave. And so it has to respond by reading the data from the master and doing something with it. The second one provides a function that the ATtiny will call when the master does a read. So in that case, the software has to do I2C writes in response to this. After that, you just call wire.begin with your slave I2C address. Let's scroll up and look at handle write, which is right here. And so when it's called, it will be past the number of bytes that the master has written. So now let's look at the heart of the function. The case where the master writes is the simplest. Num bytes will be 2. The first is the register index from 0 to 3. The second is the value to store in the selected register. Writes are handled in case 2. The software reads the 2 bytes and then stores the value v in the register selected by cur_reg. Variable registers is a union of a 4-byte array and a uint32t. If the third register is written, the software also writes the register values to variable val_to_display, which contains the value actually displayed on the LEDs, as described in my video on Charlie plexing. The case where the master reads is more subtle. In this case, num bytes is 1, so reads are handled by case 1. The software stores the index of the register to read in global variable cur_reg. Then, function handle read is automatically called. Now let's scroll down and look at handle read. It's right here. It's rather short, and you can see that it takes no parameters. Handle read does some range checking and then does the write in response to the master's register read. You can see that the value written is the selected register, or 0xFF in the case of a range error. That's all there is to it. These few lines of code make an ATtiny work as an I2C slave with a register-based programming model. My program would be more efficient if I used a bulk write model. In that case, only master writes would be allowed, and there would be no registers. Num bytes in handle write would be 3 for 3 bytes of LED value. But the register model is more typical, so I wanted to show it. Next, let's take a very quick look at Linux software for the master. Here's the Linux master software. We already saw that you can write the slave's registers from the command line using I2C set. You can also read them with I2C get. This program writes the slave's registers over and over to display a pattern in light. It runs on a Linux PC with a CP2112 USB-I2C bridge, or on a Raspberry Pi using the Pi's native I2C pins. You will have to set I2C bus to the correct value. On a Raspberry Pi, it will probably be /dev/I2C1. On a Linux PC, just observe what device appears when you plug the CP2112 in. If we look towards the start of main, we see some boilerplate code that opens the I2C bus and associates the slave address. Function doWrite actually writes the registers. It's called from main to create the LED light pattern. But let's look at doWrite itself. So we'll scroll up to that, and it's right here. Val holds the value to display on the LEDs. Its 4 bytes are written to the slave's registers in the for loop. The API call is I2C SMBus write byte data. This writes 1 byte to register I. So you see, it's pretty simple. I'll put the master and slave code on GitHub. TXS0108E boards are quite cheap on Amazon or AliExpress. This is also true of CP2112 boards. Both are nice bits of kit to have on hand. I'll end this video here. See below for links, and thanks for watching.